Okay, a lot more dizzy from that than I thought I'd be. Whew, anyways. So I just got back from seeing the Supergirl movie, and I thought it was pretty good. Was it as good as the first Superman movie from last year? No, but anyways. What I'm here to talk about today is a scene in the movie in which our hero, Kara, gets stranded on a planet that orbits around a green star. And it reminded me of a question I used to ask myself when I was first starting to learn astronomy. And that is, why don't I see any green stars ever? Green is my favorite color, and I think it would be super cool to see a star like that, just like in the movie, but I don't see any stars like that ever, and I wanted to know why. And if you watching have ever asked this question to yourself, then we can figure this out using some whiteboard science. If you ever spent any time stargazing, you'll know that when you look up into the sky, all the different little white dots at first look all the same, but then the more you look, you'll start to see that they actually do have different colors to them. There's the normal white stars like usual, but there's some stars that also look blue and other stars that look red. This is because stars are an example of an object that we call a perfect blackbody. Objects absorb and re-emit light, but what makes a perfect blackbody so special is that the way they absorb and re-emit light depends entirely on its temperature. This process of absorbing and then re-emitting light is called blackbody radiation, because it's a blackbody that's radiating light. Hello. Post-editing John here. So it looks like I actually just made a bit of a mistake with what I just said right there. Stars are not actually perfect blackbodies. They are near perfect blackbodies. There's actually no such thing as a perfect blackbody. The models that we're using assume a perfect blackbody, and stars are just so close to that they match the model really well, which is why we still use them. A fun fact I can leave you with, though, is that the closest thing that we have found in nature to an actual perfect blackbody is the cosmic microwave background radiation. If you want me to talk about that a little bit more, feel free to leave a question or comment down below. Hopefully if I make that video, I won't make a mistake like this again. I don't want to mislead you guys at all, and I'm definitely not above making an error here and there, so that's totally my mistake. Just wanted to clear that up with you guys, so if you're all good with that, I'm all good with that. I'll see you back in the video. If you own an electric stove, you've probably even seen an example of this. When you first turn on your electric stove, the coils on it at first don't seem to be emitting any light at all, they just seem like normal. But as it gets hotter and hotter, the coils start to glow red, and if they get super hot, they might even glow orange or yellow. But it's important that I said that at first they don't seem to be emitting any light. They actually are, but just not any light that our eyes can see. You may have heard the fun fact before that animals like dogs and elephants are able to hear sounds that us humans cannot hear. Sounds that have frequencies too high or too low for our ears. And light works the same way. Our eyes as humans are only able to pick up certain frequencies of light. Similar to sound, light travels on waves, and the physical length of that wave, its wavelength, is how we differentiate between different types of light. Our human eyes are only able to see and interpret a very small sliver of possible wavelengths of light. We can see wavelengths of light from about 380 nanometers to about 750 nanometers. There are 1 billion nanometers in just 1 meter, so these are very, very small distances that we're talking about. And this range of light that is visible to us, we call this visible light. And it's within this range is where we find our classic colors, our rainbow, our Roy G. Biv. But what about the light that we can't see? Here at the longer side of the light wavelengths, this is where our red is, and then beyond that, we can't see much else. So these lights, we first call them infrared. And if the light gets even longer, we call these light waves microwaves. And then if they're even longer, we call these radio waves. If the light gets too short for us to see, shorter than even our bluest and violetest of light, we call this ultraviolet light. And if the light gets even shorter and shorter, this is where we find our X-rays and our gamma rays. This map that we've made of all these possible wavelengths of light and their different names, this is called the electromagnetic spectrum. On the electromagnetic spectrum, light with longer wavelengths has not that much energy. We can kind of think of them being relaxed, like calming waves on the ocean. Meanwhile, on the other side, light with shorter wavelengths has a lot more energy. You can think of these as very frantic waves, if that helps. And we know through the colors that we're able to see that red light has a longer wavelength than blue light. So red light has less energy than blue light. And if the light has even less energy than the red that we're able to see, we're not able to see it. So going back to the coils, as the coil heats up more and more, the light that the coils are emitting, the wavelength of that light is getting shorter and shorter. So the light from that coil is getting shorter and shorter until it finally reaches a point until the light has a short enough wavelength that we are able to see. And of course, it's going to start in the red. And if it gets even more energy, it's going to get to the orange. And for stars, this works the exact same way. The red stars that you see out there in space, while they are very, very hot indeed, they are not nearly as hot as stars that are bluer in color. Blue stars are hotter than red stars. Another way we can look at the relationship between the color of a star and the temperature of a star is through something called Wien's law. So this is Wien's law. Let's break this down. This Greek letter lambda here represents the wavelength of the light, specifically the peak wavelength an object is emitting. This is the wavelength of light that the object is emitting with the most energy, so it stands out the most. This T here represents the temperature of the object. The temperature of the object is going to be measured in units of Kelvin. This is a common unit used in physics and chemistry. And the little b here is called Wien's constant. Because it's a constant, it never changes in the equation. Basically, what this equation is saying is that as the temperature of an object increases, as it gets hotter, the peak wavelength of that object is getting shorter and shorter, just like with the coils and just like with stars. As an example, let's run this equation using our sun. The average temperature of our sun is about 5,800 Kelvin. So let's plug that into this equation and then see what peak wavelength our sun emits. So plugging in the temperature of our sun into this equation, we get a result of a peak wavelength of about 500 nanometers. So 500 nanometers is going to put us about at the middle of our visible light. So if we look into what 500 nanometer light looks like, we get a result being the color green. No, that doesn't make any sense. I've seen the sun before, definitely, with my own eyes. And I'm pretty sure that the sun is yellow. I've been drawing it since elementary school. We always use yellow crayons or markers whenever we're drawing the sun, and it's never green, it's yellow. It's definitely yellow. I thought I made a mistake, but no, the 500 nanometers does look like green light, and that definitely is the peak wavelength of the sun, but that's definitely not what the sun looks like to us, right? The sun's not a green star, it's a yellow star. So in order to figure out what the heck is going on here, we need to take a look at the black body curve of the sun. Okay, so remember with Wien's law, we determined the peak wavelength of an object at a certain temperature. What a black body curve does is it plots all the different wavelengths of an object at a certain temperature and plots the intensity or the brightness of that wavelength. For our sun, the black body curve is going to look something like this. We know that the peak wavelength of the sun is about 500 nanometers, so that's going to be the top of this hill. This is the wavelength in which the light is emitted at the highest intensity or brightness. And we also know that this is just about right in the middle of our visible light, so we can draw the borders for that right about here. And because on this graph, the wavelength of the light is actually increasing as we go further this way, we gotta write our Roy G. Biv backwards up here. So it's actually our Vib G. Yor. So our green light, our 500 nanometer light, is technically, yes, at the top of this hill. But there's also all the different colors right next to it at the top of this hill. And even though green is technically being emitted at the highest intensity, there's also all the other colors being emitted at very high intensities also. Intensities very close to the green. And because the brightnesses of these colors are so similar, we kind of just see a mixture of all of them. And in physics, a mixture of all the different wavelengths of visible light makes the color white. So even though the sun is technically in a way a green star, it appears white to us. But wait a second, the sun isn't white, it's yellow, remember? It looks definitely yellow to me in the sky, not white. So what's going on here again? Do we need to look at another graph and do more math? Don't worry, I'm not gonna do that to you. The reason that the sun, despite truly being white, looks yellow to us in the sky is because of the Earth's atmosphere. As light from our sun travels on waves all the way through space, through our atmosphere, and then into our eyes, the elements in our atmosphere deflect some of that light. This is a phenomenon called Rayleigh scattering. With Rayleigh scattering, shorter wavelengths of light actually deflect much easier than longer wavelengths of light, so they're the ones that are going to get deflected first. And this is going to be our blue light. So as the waves of light pass through our atmosphere and into our eyes, the blue light from that visible light is going to be scattered first. So despite it being white to us, because it's going to be all wavelengths of light coming into our eyes, it's shifted a little bit because there's less blue in there because it's being scattered. And because the light is going to be a little bit less blue, that's why it appears yellow, because yellow is at a longer looking wavelength. Rayleigh scattering is also one of the reasons that our sky looks blue to us. And also, when the sun is setting on the horizon, the angle between the sun and us standing on Earth is bigger, which means that the light from the sun is actually passing through more atmosphere to reach our eyes, which means even more scattering, which means that the light from that is going to look at even longer wavelengths. This is why sunsets look yellow and then orange and that beautiful deep red as the sun is finally setting on the horizon. And if you were on space, like in the International Space Station, and you wanted to look at the sun wouldn't look yellow to you at all. It would actually look pure white, like we would expect. This is because there's no atmosphere up in space to scatter that light with Rayleigh scattering, so the sun really does look white to them out there. So, to answer my old question, and hopefully yours, where are there green stars? Technically speaking, right up here in our sky there's a green star. But that's not the whole story. Green stars kind of exist, but not really. Stars can only technically be green if they're around the same temperature as our sun, and therefore around the middle of our visible light spectrum at this certain nanometer range. But despite peaking at green, there's a bunch of different colors at very similar intensities right next to it, so it's all going to blend together to look white. When you have a really, really hot star, it's going to look blue. And when you have a cooler star, it's going to look red. And if you have a star that's sort of a medium temperature, it's going to look white. So in our quest to learn about where we could find green stars, we learned that there technically are green stars, but also kind of not. We learned about black bodies and black body radiation. We discovered the electromagnetic spectrum. We used Wien's law to determine the peak wavelength of our sun, and we also took a closer look at the black body curve of the sun to determine that despite peaking at green, it's actually more of a mixture of these colors right here in this tiny little range. And that's why it would appear white to us. And by looking at the phenomena of Rayleigh scattering, we learned why, despite being white, the sun looks yellow to us in the sky, and why it seems to change color as it gets lower on the horizon in those deep, beautiful sunsets. And all of this we learned from just asking one simple question and doing some whiteboard science. If you think I didn't explain something well enough in this video, or you would like me to clarify on something, please feel free to leave a comment below. I'd love to talk to you. And if you have any other questions about the colors of stars or the rest of our universe, please also leave a comment below, or you can contact us at this email right here or in the description below. But no matter what you do, always keep asking questions and always keep looking up.